Welcome back to 3 Deviations. So, integral calculus, it's been interesting. So, we've been really thinking about integral calculus as a method to find the area under a curve. Well, yeah, that's admittedly pretty cool. Finding the area under the curve, under a smooth, continuous curve, is a pretty cool thing that we can do, but it's not the only thing that we can do with integral calculus. So today we are going to be talking about something called the net change theorem, and this is going to kind of open your eyes to the applications that integral calculus can have. Now, it's not going to cover everything. We aren't in an application unit yet. The purpose of this is just to open your eyes to what integral calculus can mean. Now, we're not going to do any examples, but I do want to show you some of the application fields where it's available. But don't worry, in future videos we will definitely be covering some more applications, but that will come in units 5 and 7. Alright, so let's talk about the net change theorem today. So the theorem really talks about how you can apply the fundamental theorem of calculus part 2. And this is the net change theorem. It shouldn't look like anything new. It says that the integral from a to b of capital F prime of x dx is equal to capital F of b minus capital F of a, right? This is the fundamental theorem of calculus part 2. It says if I have a curve, right, if I have f of x, so that's capital F of x, and I have endpoints a, I have endpoint b, I'm going to find the area here, I take the antiderivative, this f prime of x, find the antiderivative, and I evaluate. Pretty easy stuff. But now we can apply this to multiple situations. I'm going to give around 4 examples right now, but there are many more that we'll cover. But basically, these are some of the really big fields where we'll see integral calculus, or more elementary integral calculus, applied. So here we'll talk first about some flow rates. So flow rates writes the fundamental theorem of calculus as the integral between t1 and t2 of v prime of t dt as being v of t2 minus v of t1. So it basically talks about continuous flow. So let's say I have some sort of volume here, and I have fluid in here, and the fluid is leaving. The fluid is leaving with some rate, v prime of t. And if I want to find the net change of that, well, then I'm going to take the integral of v prime of t dt, and then I'm going to find whatever endpoints that I may have. I'm going to subtract, and that's going to give me my proper volume change with that continuous flow. Now we can talk about a field in chemistry, which you may have seen already. So this is reaction rates. So if I have the integral from T1 to T2 of the concentration of C prime with respect to T, then that's going to be equal to the concentration at T2 minus the concentration at T1. So this thinks about rates of reaction. So what's the concentration at a certain time? If I have some sort of rate going from some initial state to a final state, then that rate is going to be C prime of T. Then again, I find that net change by taking the integral of C prime of T with respect to T between my endpoints. That gives me the net change. All right, so now we've got another example. This is more of a physical example. So this talks about the linear density of an object. So if I have the integral from a to b of a density function, rho of x dx, then that's going to be equal to the mass at A minus the mass at B. So if I have some sort of rod, because this is linear density, and I take an A and a B, and then my density is laid out by rho of x, then my total mass is going to be this whole thing integrated along rho of x dx with my endpoints, and again that gives my net change. All right, so we've got one more example that we'll cover through. I know this is really just drilling in the fundamental theorem of calculus part 2, but it's still good to see some examples where we're not dealing with just f of x, right? So population growth talks about the change in population, the total net change in population over time, and then we check that continuously. So I have the integral between t1 and t2 of n prime of t dt equals n of t2 minus n of t1. So if I have a group, of guys here, and then that goes over here, and then it becomes a group of even more guys here. Maybe it won't look like more guys, but let's say it's more guys. So I've got more little red, maybe these are these little red mites that show up on the porch. So you have a lot more red mites on the porch here than we do there, and then that changes by n prime of t. And then again, to get the total net change, integrate n prime of t between my endpoints with respect to t. That gives me my net change. All right, so that is the net change theorem. I hope I drilled that properly into your head. This is really a preview of what's going to be to come in not as much Unit 5, but really Unit 7. We're going to be talking about a lot of these applications to sciences. It'll be a lot like the end of Unit 2, where we were talking about the applications of differential calculus, but of course we'll be doing it with integral calculus. All right, so in the next video we are going to introduce our final topic for Unit 4. It's going to be a big topic, and it's going to be our first indefinite integration technique that we will be covering, kind of similar to the reverse chain rule. All right, so we'll talk about that in the next video. See you guys later.